I just want to point out before I start, for those of you who didn't see it already, I would like you to at least write this down somewhere. This is where we're going to post all the information about where the videos end up and where the code and so forth ends up, okay? In particular, since today I'm going to be talking a lot about implementation stuff, I'm going to post something to there later, which is a pointer to a pre-built version of MIT Scheme for Ubuntu, specifically ghardy, that you can just install on your local workstation and use. Okay, it should be ready to use that way. And it's designed for the 64-bit version. So if you have a 32-bit version, we can do something else, but just let me know. So.
Would you pronounce that? I can't actually read the whiteboard.
Oh, sorry, Symbolic-seminar.
As a mailing list?
It's a Google group. So yes. I think they're the same these days.
Right.
Okay? All right, so today I'm going to start off, I'm going to be talking a bit about implementation of the things that, in particular, the stuff that Jerry and Alexei talked about yesterday. I'm also going to talk about some variants on the implementation. There's one that I did, basically stopped working on about a year ago, that is not quite as nice as what they did in some ways, but is nicer in other ways. And in particular, it has a compiler that will take scheme code and compile it into propagator networks, which is sort of we imagine the way propagator networks being used most of the time is that you write stuff in some higher level language, you compile it down into networks, and you run the networks, okay? But I'm going to start by talking about how Jerry and Alexei's implementation works. And to motivate this a little bit, I'm going to show you in a short example. Since we've already talked about this yesterday at length, I'm not going to go into a lot of examples. One thing that, if you want more detail about the examples and about some of the motivation behind this stuff, there's a paper that these guys have written that, again, will be posted to Symbolic Seminar. And you can read it, and it will have all the code in it, and it will have more examples. And it'll talk about a couple of things that I'm not going to cover today. Okay? So the example here is, now this is Heron's, what is it called? Heron's algorithm for refining.
What people always call Newton's method.
Newton's method, yes.
For
square roots.
Invented by Heron of Alexandria in 20 BC.
So this is a step that will refine an estimate for a square root. Okay? And the way you read this thing is that you have this thing called Heron step, which has 3 arguments, and these arguments are going to be cells. Okay, so we're talking about building a propagator. And the way the propagators work in this system is that there are procedures that accept cells as arguments, and then they create themselves, basically, and hook themselves up to the cells that you hand in. Okay? So we're going to have cells called X, G, and H. We're going to make what's called a compound propagator, meaning that the body of it is a collection of other propagators that are glued together in some pattern. And the compound propagator takes one argument, which is a list of the inputs. It's not really the right word. It's in fact the cells that it needs to monitor to determine whether it can do anything. Okay, they may not be strictly speaking inputs, but they include everything, every neighbor cell that if it changes, this thing has got to do something. Okay? So in this case, H is not going to be one of those, so we leave that out of the list. So we have just X and G as the inputs. And then we have some internal cells that we're going to create at the very beginning. Okay? And then we're going to hook them up to various primitives that do stuff for us. So we have a divider. We're going to take a divider that has X as the numerator and G as the denominator, and it will spit out its output into this thing called X over G.
Is there a reason why you didn't overload using generics to overload the math operators on cells to do this?
Well, the arguments are different. Okay, these are not, this one has this is not an expression-based operator. Okay, so it's not, what you do is one of those arguments is the output. Whereas in the ordinary generic stuff, all of the arguments are going to be inputs, and the result is the expression result. Okay, so it doesn't quite make sense. We do this thing, I'm going to show you some generic stuff,
Okay.
but we're wrapping it in these propagator things which have a somewhat different signature.
This is the wiring diagram.
Yes, we're building a wiring diagram, and I'll draw this on the board just for fun. But basically, okay, so we have a divider, we have an adder which takes two things and adds them together. We have a constant, a 2 constant that we have to build that way and put its output into a cell. And then another divider that takes the output of the adder and the 2 and puts that out as the H, the new estimate. Okay? So let's see if we can draw this and make it make sense. Okay? So overall, we have this big box. And coming into the box, we have an X and a G down here somewhere. And over here, there's some sort of an H. And so the X and the G go into a divider. So let's draw a divider, maybe like that. Okay. The output of that goes into an adder with G. All right, okay. The output of the adder goes into a divider here. And I suppose I should make the little circles that Alexei had on his boxes yesterday, so when it matters. And over here we have a special thing which is a 2, and it goes effectively into there. Now what I didn't draw here, and I'm going to, is that in fact there are these cells. Okay? So we can't just directly hook these things up to one another. Instead, actually let me try to be a little clearer here. All right, let's call this constant 2. Okay? And then what we have to do with these things is we have to put cells in them, because that's where the values go. Okay, and that's where we're going to do things like remembering stuff. That one is not there. Excuse me. I'm winging this, as you can maybe tell. So I'll have right, and there. Don't need the second one. Sorry.
Constant 2.
The constant 2 is a propagator, and its output has to go into a cell, which it does, which is called TWO. Okay, kind of arbitrary. Okay, so we want to attach the labels. This is X/G. This is TWO, and this one here is G plus X/G. Okay, and so this is what that code is implementing, that particular diagram. And I'm not going to step through how it works. It should be hopefully not too terribly hard to see. And we can plug this into the system. And let's see. Why is it not stepping? Thank you. Okay. And we can give it, basically hook it up to some other things. So we hook, in this thing, we hook up that diagram to particular cells. We make some new ones. So we make a cell here, and we make another cell here called guess, and X, and better guess over here. And we plug in some, we hook, the Heron step argument says take X, guess, then better guess, and instantiate one of those. Okay, and then after we call Heron step, then we have this complete network all set up and ready to go. At which point we can stuff in some stuff in values like 2 and 1.4. And once both of them are in there, it'll crunch for a while, and then at some point some other argument, some other value will come out here with some other things in it. It's supposedly better. Okay? Hopefully I've bored you all by now. So that's not complicated. That's just wanted to work through it once. Okay? So now we want to take this thing and put it together into a loop. And here's a diagram that comes from Jerry and Alexi's paper. And so we're going to take the Heron step that we just built here. Actually, I should probably use this one, since I think more of it is on the camera. Okay, so we take Heron step over here, and we're going to plug it into a loop, which is an iteration to iteratively evaluate this thing to try to drive it towards a better answer. Okay? And we're going to use a special thing here called good enough, which is a test to decide whether or not the result we have is adequate for our purposes. And then here we have a recursive copy of the thing we're running. And this is sort of where things get interesting. And then we have a bunch of switches, and there's an inverter, basically. Okay, so basically the switches are responsible for feeding the appropriate side of the conditional. You can kind of imagine how you would write this in scheme code, okay, or in any language. But the switches basically control the flow of values through this circuit, so that when you do get to the terminating condition, you don't keep on buzzing, trying to produce better and better answers. Okay? So this, yes?
Just to clarify, the switch goes up if the input is high?
Yeah, it ought to have been marked, I suppose. That's true. So there's a T and F, and I believe that the top one is T and the bottom one is F. Let's see, is that true?
Yes.
Good enough would mean that, yes. So T, that, if this one's true, the input here, these are the inputs to the switches, then the top one will be if the input is true, and the bottom one is if the input is false.
They're really all SPST.
Yeah, you don't really need both sides of those. Is it just me, or is it still hot in here? It is still hot in here. Come on. That. Oh, I see. It's the time. It's going to shut itself. No, it'll be all right for now. Well, hopefully that'll keep for a while. Okay, so this is this funny thing. Now there's a. So this part is interesting. So what does it mean to say that we have a copy of the thing that we're doing? Okay, and the answer is that you can see in the code, which I'll show you now, is that basically you just call this thing again. Okay, so here we have that call right there. Okay, we're calling itself. Now that is weird, okay? Now the only reason this works is that it is the instantiation of that particular propagator is lazy. Okay, so if there are never any inputs, if you never provide inputs to a full set of inputs to this thing, it will never be instantiated. So that's what stops it from, basically using up all your memory and producing nothing. Okay, now, do I need to go through all of this? Does everyone here sort of see what's going on? Should I? I don't want to belabor the point. Okay.
To the wiring diagram.
The wiring diagram, and this is the textual code that generates the wiring diagram like this. Okay? And hopefully that's not too hard to see. And then we have another one. Here is another diagram to implement the good enough test. And finally, we build a square root network, which basically initializes the iterative loop, starts it off with the guess of 1, and then runs it for a while. And you can hook it up to some input, and it'll buzz for a while, and eventually you get an answer out. The answer is not too bad. Yes?
That's interesting. So why didn't you just make the output cell the same as the guess cell?
The output cell the same as the
Yes.
guess cell.
Instead of having recursive instantiation.
You have to have the recursive instantiation to make it work at all, but yeah. Well, in this particular case, the problem is that you've got a cutout, right? See? Yes, here, make the answer be just directly hooked up. That might work. Now that I think of it, yes. You have a point there. You could probably just hook them up. No?
So you if you had a way to know that after you went around the loop once, you produced a better value for that cell rather than producing a different and contradictory value for that cell.
Well, it's a question of how merge works,
Right.
is what you're saying.
So you need
Merge
two-
would have to be
you
hooked
sort
up.
of need two outputs. One is I'm done, and one is the current
So
one. plus yes.
Well, you need a done detector somehow, somewhere, but that could possibly just work out. But the thing you'd have to do is modify merge so that it has some idea that the 1.0 was
That there-
a guess and the 1.4 is a better guess and the 1.4, 1.4, 1 is a better guess.
So I think the answer is that that if you think about this in terms of cells that you can use side effects on, then what you're saying makes sense. But that's not the underlying programming model here. The underlying programming model is that there are no side effects. Okay. The fact that there are no side effects in this code, other than when you're sitting at the at the computer typing at it. You set it up and it does its thing, and it basically just propagates. And so you need you need copies.
And you can have virtual copies, of course.
Yeah, and that's what the thing. If you reuse the same cell and tag the copies somehow, tag the values, that would give you virtual copies of the cell. Okay.
And you can do
But it's
that.
still not time
You can do that
dependent.
even with the dependencies of some level.
Yes.
Introduce a concept of conversion, which is if you have something that takes the same time to propagate
Yes.
over, then you can pair them together and merge with.
Yes, and that's sort of another virtual copy mechanism again. Right. I
One
mean,
of the ones I prepared for the class last year teaching actually did that.
So this particular implementation uses a physical copy of the network to do various things, but there are virtual copy mechanisms that people have invented to do similar things. And ultimately you do have to have some sort of copying going on, and it's, there's lots of ways to do it. But the way to think about this is that the implementation of this language is side effecty, but the design, the specification for it is that it doesn't have side effects.
It's
Okay.
single sign. Yes.
Well,
Which,
except that if you're programming inside of it, you shouldn't really be able to tell, I think.
That's not
Is that
even
true?
single assignment, it's incremental refinement.
exactly.
It has to be a refinement.
Has to be a refinement.
There has to be more information.
Yes, you have to, basically, you're right. Because the problem is that if you start thinking about side effects, then all of a sudden you have race conditions, and there shouldn't be any races here. Right? You have to design, it has to be built in such a way that races don't happen. So,
The content of a cell can get more and more specific. Okay, but it's about then it has.
well,
to-
we're not even there yet.
merge-
We're not at that part
merge
yet.
has to do that, right.
We're not at that merge yet. So,
What you've shown so far, I could make a network that has a race condition.
Yes, you can.
If I sat down and thought about it, that would be an error on my part, not,
well, only if, it depends on the implementation of the merge in your system, and I haven't shown you that. And unless you have some particular implementation in mind, then I don't think that's true. Okay? So,
Some kind of master-slave scheme.
sorry?
You can probably use some kind of master-slave scheme
Can you speak louder?
Yeah,
some kind of master-slave scheme
a
to.
master slave scheme,
So
which is,
if you're building a flip-flop, one
Yes.
of the problems is that you get periodic spikes, and so you.
metastable states, that sort of thing, yeah.
Yeah,
Yes,
that's a
that's a
method of-
different kind of,
That's a method of actually clobbering a value. Here we're talking about, these values don't go away, right?
right. There's no actual, there shouldn't be any real sense of time in here, right? Which is why, because this thing doesn't actually have a model for time, there shouldn't be any model for side effects, because time and side effects are roughly the same thing, right? Anyway. Okay, so how does this work? Well, here is, I think Lexi showed you something very much like this yesterday. The key thing being this merge operator here, that is the thing that decides how content is attached to or merged into cells. And there's some other bookkeeping here to do this, to attach neighbors, okay, which basically is going to say, well, you attach a new neighbor, then you add it to some list, and you tell all the neighbors that they should maybe wake up, okay? And I should note that I'm not going to show you the scheduler because I don't understand it. If you want to know about it, you can look at the code, ask Jerry and Alexi who wrote it, and anyway. Okay, and then this thing is basically Jerry's favorite object-oriented programming hack. Okay, or really a messaging hack is what it is. So you can send messages to this cell to get operations on it. Okay. And the other side of those messages are here. Okay, so we hide the messaging. And then there's a couple of fixed constants that we know about. And the one for contradictions is made generic because later on we're going to take advantage of that when we have different kinds of contradictions. But nothing is always nothing. There's only one of them. And here is the generic merge. But so far, all we've really done is we've said that there's going to be some kind of we're going to allow one value, and we have some sort of an equality operator here. And if you try to put the same value in, then it doesn't do anything in particular. And if you put in two different values according to equal, then you get a contradiction. Okay? And then there's simple cases. The bottom two operations are basically to say, well, if one of them is nothing, and the other one is something else, then use the other one. Okay? Use the non-nothing. And here is, okay, so now I'm going to talk a little bit about primitive propagators. This is the basic mechanism. All a propagator really does at the bottom level is it hooks itself in. Okay? It hooks itself into the circuit. There's question marks over here next to alert propagators because, as I explained to Jerry earlier today, that's not necessary because if you go back to the cell, that's being done right there.
Unless
New neighbor.
list is empty.
If the neighbor list is empty, then there's nothing to do.
But it might possibly
All right, well,
construct some more network when you run it.
in which case, then that should be conditionalized probably. Anyway.
But it doesn't hurt.
Doesn't hurt, unless you're worried about constant factors. So, and then here's a thing that takes a procedure that is a functional procedure, something like plus, and converts it into a primitive propagator. Okay, and so here is it's going to basically create a procedure that takes some number of cells. This is a little sloppy because it's not doing anything about trying to figure out whether function is limited in the number of cells that it can accept. Okay, most of the functions we're going to put in here will require at least one cell. And then it separates the cells into inputs and outputs and makes a new propagator with the appropriate inputs, and then it builds this action. So this is just the thing that gets run when the cell is woken up. And all it does basically is it does some computation to decide if it should run F, and if it should run F, it runs it, and it gets some information and it merges it into the cell with add content. Okay? Trivial, hopefully. And you can then go about building simple things like plus and minus and all that stuff. And we're using generic versions because we'll hack on them later. Okay? And constants are another one of the same, except no arguments. And let's see, here's something more interesting. This is how conditionals get done, and the switches as well. So a conditional basically is a thing that has a predicate input and it has two outputs. And what it's going to do, two inputs and an output. And it's going to use the predicate to decide which input to channel to the output. Okay? And so it does the appropriate thing here. Basically looks in the content of the predicate input. And remember, this thing is not going to run unless, well, in this particular case, it's not going to run unless at least one of those things has got a non-nothing value in it. Okay? And so it'll then decide whether or not it's going to make a change and make the appropriate change by shuffling the values around, shuffling the content. Okay? And a switch is a variant on that thing that has basically, this is an SPST switch is what you're saying here. The other one is a SPDT, for those of you who know what that means. Okay, and here's the trick with compound propagators. The compound propagator basically is a regular propagator in the sense that it has the same, very similar arguments, but it's got this cutout here that basically makes it evaluate itself lazily. Okay, so the lazy cutout is going to say what, if you have, it's only going to do it once, so that's what the done is for. That's the thing that makes it run the builder once. And then the other thing it does is it looks to see if every neighbor, so if any neighbor, this is really backwards, so it says, no, that's every nothing. Did I do that wrong?
If done or everything is nothing, don't do anything. Otherwise, if anyone...
This is backwards. I screwed it up when I screwed up the slide. Excuse me. Any. Yeah, I made a mistake. When I folded the code, I made a mistake. Anyway, so it should be any. Yes, if there are any inputs that are not nothing.
Well, that way it should be if it's not done and something else is not nothing.
Yes, that's right. Okay, to negate that entire thing. That's right. All right, so I blew it. Alexi's code was correct, and I messed it up. So, mea culpa. Okay, so you basically just, when you have some inputs, and you build the thing, and then after that, you just leave it there. Okay, so you build it once. That's just the thing that prevents recursion from screwing you. Okay, so here, we can now go and start generalizing. We can add interval arithmetic, like the stuff that Alexi was talking about earlier, yesterday. And basically all we have to do is define some operations to do interval arithmetic, and then we make handlers for them in the standard operations. Okay, that's most of it right there. And the only other part is we have to define merge for intervals. So we define merge, and it's pretty much the same thing. We have simple ones that combine numbers and intervals, and all that cares about is whether or not the intervals, the number is inside the interval. And then otherwise we do this slightly more complicated thing that ends up doing a kind of an intersection. Okay? And that's all of it. That's the whole story. Okay? So we just added intervals to our networks that simply. And likewise, we can do something hairy we can add this thing. I'm not showing all of it here, I think. Is that right? Yes. So this thing adds what we call supported values. And a supported value is basically some value that has a justification attached to it, a thing that says, I believe this because. Okay? So you can imagine every one of these things being some, let's say, a number. And in addition to the number, it says, well, this number was derived from the following computation that, and ultimately there are some assumptions in the computation, and this is the list of assumptions. Okay, so that's the support for that number. Okay, the support is basically why you believe that this number is the correct answer at this point. Okay? And what we want to do here is a little bit more complicated of a merge. Okay, because what you need to do is that sometimes you need to merge the support. And that's why this is hairier than the standard kind of equality test. Okay? So we're going to be looking at here, we have a thing called value of, which will tell us the value of a supported value. And then there's another thing which I suppose doesn't show up here. There's another operation called support of, which produces the support. I'm not going to tell you how the support is modeled. Just as, you should understand that these things are there. You can imagine it being a set of things, and that there are operations that you can do on the support, such as intersecting the set, or there's a kind of what's the word we're using for it? Senior moment. You can determine whether a particular set of support is subsumed by some other set. Okay, that's the word I was looking for. Okay, so basically what we want to do here is we're going to say, the first thing we're going to do is we're going to merge just the values by a recursive call to merge. And if it turns out that the merged value is the same as the old one. So in this case, remember the SV1 here is the old contents of the cell, and SV2 is the new. Maybe the names should reflect that. But so if we haven't changed the value, then the question is, do we need to do anything with the support for the value that we have here? In other words, do we have new changes to support? So we go and look at this thing and says, well, so this one is basically saying if the merge of the two values is the same as V2, then now you have both values, the old value and the new value, are the same. So all we'll have to do is manipulate the support. So which one is more interesting, more informative? And usually that means smaller. Okay, so the support there'll be a narrower set, and you choose whichever of these supported values has the smallest support, because that's a subsumption of the other one. Okay? And otherwise, you're just going to keep the old value because you haven't done anything that's going to help. There's no useful information there. Now, if the merged value is not the same as the old value, but it is the same as the new one, then the new one's better. We want that one. Okay? Because that effectively subsumes the old one. Otherwise, we do something more complicated, which is that we were going to take the merged value and merge the supports for both of them. So, and that could either mean, yes, it's supported by all of these, or it's supported alternatively by one or the other. There's a variety of ways you can do support. Okay, this doesn't say how it's done. And then the only other thing here is this notion of contradictory. And this is basically why we needed to make that generic, is that now we're saying the support doesn't play a role in whether something is contradictory, only the value. Okay? So that's it for this part of the talk. Now, next I'm going to move on to talking about this other implementation that works quite differently. Alexei. I am not sharing the truth maintenance system. I made a deliberate decision not to do that because it is very hairy. I think it'll be hard to fit into slides easily. And if it is very pretty, I agree. But if you want to look at it, read the paper. Okay? This is what's called a loss leader. Okay? We're trying to get people to read your paper. I'm helping you. Yes.
Before you move on,
Yes.
silly question. Can you
Good.
stick a number into better guess and square it?
You stick a number into better guess and square it. Well, is it reversible? It should be. If these are not constraints, you know. Okay, the way this was built, these are unidirectional propagators. But if you were to change them into constraints and leave this one empty and put that one there, well, what will it compute? Multiply by 2 to get there, and then it will subtract whatever's in that. But this one won't have a value. So I think it actually won't go anywhere because there's no way for you to go make the step backwards across here.
That's too bad. That would be cool.
Well, maybe you can invent a better step. Yes.
If you define a merge which for a value and an error prediction, so you can compute the error on your square by subtract, you can compute the square of the error.
Well, that's like basically equivalent to interval arithmetic, isn't it?
Yeah, well, it's not, it's different from interval semantically, but
Okay, but
the merge operation would probably be somewhat similar.
What was this?
Right.
Which one?
So basically, is a combination of a value and error bars, basically.
Some proxy for error.
Some proxy for error.
Such that if you were to
I see. So you want to put in like a symbolic epsilon or something like that?
If you were to define
Yeah.
that proxy by the error, the resulting function would be monotonic.
Yes.
Is basically the thing. And then
Okay.
you know that your proxy is comparable.
Yes, I think that's right. You could certainly, with the underlying arithmetic well, not in the standard scheme system, but in the one that Jerry has built, you could certainly do symbolic stuff like that.
Once you've got that, can you then tie your H back into guess? And
Why?
have it work meaningfully without copying the network?
Yeah, I actually think so.
Without copying the network.
Yes, what he's worried about is the thing we were talking about a few months ago. Actually, a month ago. We got a feedback since we're doing, yeah, it turns out you can. It's the merge then becomes, in fact, the right thing is merge becomes average, approximately, and then you have what looks like an analog computer where the ES gets better and better. And that works, okay, if you can.
Cool. After all these years, we're back to analog computers.
And what happens is, if you have a network that's really interesting, good hack, is you could have this network which is a propagator network, okay, and it's hooked up like this, and it has an output, well, output has another propagator network it's connected to, and the other propagator network is you can make use of the initial approximation, and as the approximations get better, it actually improves what it's doing. By golly, that'll work. Okay? And it looks just like what happens in analog computing. Okay? And we can make that happen. We were fooling with that.
It's probably after my time, so I
Yeah,
didn't.
that was about.
I'm not aware of this
It was
one.
about October that we were talking about this.
Okay.
So at the beginning of your talk, you said that they had thought about ways of compiling the standard language into propagator networks.
That's what I'm doing next.
But one of the values of propagator networks is that you have more expressive power.
Yes.
So what value do you get out of compiling into that?
First of all, you get the ability to write scheme programs that have extra semantics, so that you can do things like dependency-directed backtracking with optimal backtracking.
Okay, so you weren't talking about just
I was trying-
straightforward scheme. You were talking about.
Well, once you add AMB into scheme,
Right.
which you can do anyway, but if you do it without some sort of substrate like this, the AMB will be non-optimal. It will not backtrack optimally.
Right.
Okay, and this will allow you to do optimal backtracking. And that was sort of our original goal for building this stuff, but it's now turning out to be more interesting than what we set out to do. Okay, but I guess what I'm sure the answer to your original question, I think, which was why would you want a high-level programming language that throws away most of the useful functionality, is maybe you don't, but we don't yet have a language that can exploit it, other than this stuff I'm showing you, which is basically assembly code.
Well, of course, it's true in assembly language. When you go to something like some higher level language, you probably all the possible functionality that's in the assembly language, which is insanely more than you think of. Nobody
Yes.
sits around and does bit shifts and manipulations.
Well, that's true, but you could imagine that there could be languages that are more powerful than what we currently use.
Sure.
That would fit onto this framework, and we just haven't invented them yet, and maybe that would be fun.
This is a substrate like it.
Yes. Yes.
So back to the issue of overloading using generic operators.
Yes.
The thing I was thinking of was, let's say you have a plus, and you overload it so that it takes 2 cells as input, creates an output cell and a propagator that connects all 3 of them, and then returns the output cell as its result.
Yep.
So that you could chain together,
Yep.
Complex
You could do that.
expressions,
Yes.
or in this case, they wouldn't really be expressions, more like equations, statements of relationships rather than the things that get used as an answer.
You could certainly do that, and you'd run into, you'd start having to doing things like multiple value return when you had things that had multiple outputs, and yes, you could do that.
And
Yes.
there is a problem in SICP that has people doing that.
Oh, okay.
In chapter 4.
All right.
No, chapter 3.
Okay. Plug. SICP. Go read SICP. It's online, by the way.
Exactly.
Any of you who didn't know that, the entire content of the book is free and online. So search for Structure and Interpretation of Computer Programs. Okay, enough plugs for now. All right, so the next thing, I want to talk a little bit about compilation, which compilation is, I'm going to show you fragments of a compiler, and most of what I'm going to show you is not very interesting because it's all about scheme, and very little of it is about the stuff that gets generated. Okay? So, and unfortunately, scheme, when you add in certain things, certain kinds of operations, like you can see this define here. That's what gets done for, basically have these local internal defines cause some structural problems with the compiler that if you didn't have them, if you didn't have a local define, you would have a simpler compiler. But I'm going to show you what I have. So here's a thing that basically takes some scheme expression and then this thing called SENV, which stands for the syntactic environment, because this is a compiler and not an interpreter. So this is not the runtime environment. This is the thing that tells the compiler the structure of the environment at runtime. Okay, so it's going to include things like keywords for things like if or lambda. And it will also include variable bindings to show you their structure, but they won't have any interesting values. They'll just have a thing that says, yes, this particular free symbol, free identifier, is just a variable. Okay, Alexi?
Would also have macro definitions?
This one doesn't. You could. There's no reason you couldn't put in macros, but why would you want to do that for a toy? I mean, it's just a lot of hair to put in macros.
If you were building a compiler, you would put macro definitions.
If you were building a real one, you would put in macros, yes. But this one does not have macros because I just didn't want to mess with it. It's not worth it. Okay? So this is the top level thing. So you hand this thing an expression, and it is responsible for producing a propagator network that implements that expression. Okay, and that's all we're going to do here. We're going to basically take scheme code, and the output of the scheme code is a propagator network, and the propagator network has a particular structure to it. Okay, and I'll explain that shortly. So there's this thing called this guy called compile form, and in the Lisp community at least, there is a distinction between an expression, which is a thing that produces a value, and a form, which is more general and might include things like define, that are not in fact, they're not expressions, they're not even things that you can put them as an argument to plus, for example. It's just something that is part of the syntactic structure of the program. So a form is something else besides an expression. Okay? And so it calls this general compiler that does something, and then if it looks at the output of this thing, and there's a particular distinguished value called DEFN, and which is shorthand for a definition. And so if the thing you handed it happened to be a definition, then it's going to do something special. So, and otherwise it's going to just return whatever it returned. So this thing will construct what we would call a top-level definition, which when run will do something appropriate to some runtime environment that it's maintaining that holds the values of things. Okay? And if you want to compile something that is an expression, then basically it's the same thing, except that if you see a definition there, it's not allowed. Okay? And in this particular context, the only kind of thing besides expressions are definitions. If we had macros, then macro definitions would have the similar kind of a similar status. Okay, a macro definition doesn't have, or a binding of a macro is not an expression. Okay, so it would be another special case. Okay, and then I'm going to do this slightly different order. So here's the basic compiler. Okay, this is the thing that does all the work, and it's a sort of a standard kind of scheme compiler, Lisp compiler. It distinguishes between things that are lists, or symbols, or constants. And those are the three cases that matter. And an example of a constant is something like sharp T or sharp F, which are schemes Boolean constants. They're self-evaluating constants. Or a string, let's say, a string literal. A number is another one, that's right. Symbols, when they're not quoted, are treated as identifiers or variables. Or they might be keywords in particular. But in this case, when you're looking at the top level of a form, what you're going to do is you're going to look up the contents you're going to look up the symbol in the syntactic environment. Okay, and if it turns out to be a variable definition, which it's supposed to be when you use a variable reference, then it'll be okay. And otherwise, if you get anything else there, then it's an error, because you shouldn't have written that symbol there. The anything else would be something like if, let's say, which is not a variable. It's just a piece of syntax. Okay? And then when you have a more complicated thing, the first thing you want to do here is you want to make some sort of a determination. This is a little hairier than it needs to be, I suppose. So what this basically is going to do is it's going to look at the first thing in the list and try to decide if we're looking at a special form or a procedure call.
This is the operator position.
It's the operator position of what we call a combination. Okay? And the hair here is that we're looking to see if the input, if that operator is in fact a keyword, which is an internal structure of the compiler that is used to represent syntactic entities, syntactic keywords. And the only reason that this code is here is because there's some optimization somewhere else that builds intermediate expressions that have keywords directly in them. Okay, which is it's a crock, but it's just the way it works, and I'm not going to apologize for it. Otherwise, you're going to look this thing up, and somewhere along the line here, you're going to say, okay, you get some value back that is effectively the syntactic value of that operator position, and you're going to say, is it a keyword? Okay, is it if? Is it, define? Is it lambda? Is it one of those things? And if so, then you're going to just take the whole form, the syntactic environment, you're going to give it to that keyword, and it will do some appropriate thing. And I'll show you a couple of simple keywords later, but that's how the syntax is done. And if it's not one of those things, you're going to do a standard combination, a function call, procedure call. Okay? And you do that by compiling the parts of the form as expressions, and then just building this special propagator here, which is a procedure call. Okay? And that was the first interesting thing I said, unless you're interested in scheme compilers, which is not what we're really supposed to be talking about here. Here are some keywords. There's in yet another instance of language layering, I built a simple little, basically a rule system for defining the keywords. So there's a pattern matcher in here that is, I think, a standard one that we used in the class. We have a handful of them that we just toss around for various things. And this basically says if you see the keyword for quote, which will eventually be bound to the quote symbol in the syntactic environment, has a pattern, as basically a rule system that says, okay, if the tail of the quote, the footer of it, has that form, in other words, a list with one element, and that element is some arbitrary thing, then match it, bind it to the name datum, and execute that expression. And this compiles into some complicated pattern of things that knows how to extract the variables from the pattern, and gets them in order, and calls some procedure that has free variables, a free variable named datum in it. Okay, and you don't want to see that. I could show it to you, but it's macrology that bends my brain too, so it's just not worth knowing. And here's a case where, in the case of define, okay, we have a couple of different forms for define, one of which is the standard one where you write,
Sure.
here, I'll just draw it for fun, make sure that, all right. Okay, so define has got two standard forms in scheme, one of which is that you give it some name like foo and 3.14, okay? And the other one where you can write define foo of x to be times x3, which is equivalent to define foo lambda of x times x3. Okay? So this handles both of those cases. And it ultimately ends up calling this thing that makes a special value that will then be propagated back through the compiler to a place where it can be used, because at this point we can't actually determine what the right action is. Okay? And in particular, the reason for that is that at the top level, if you have a define at the top level, it's a special operation that modifies the top level environment. And if you have a define that's internal to some other lambda expression, it gets converted into a letrec, for those of you who know what letrec is. Okay? And then we have lambda, which is basically the same sort of thing. It's interesting because it actually extends the syntactic environment by adding new variable bindings. And it has a special compiler that is for compiling the bodies of lambda expressions that knows how to do the letrecization of those definitions. Okay? Let's see, there was some, and here's the code for the compiler for the body. Not too exciting, except it eventually calls that. And I don't think there's anything else very exciting going on here. This is all just the machinery. Okay. So, runtime. That was the compiler. Now I'm going to show you the propagators. A few of them, not all of them. So this language, this is built on a different propagator system than the one that I showed you earlier. That has some different characteristics. And in particular, the main thing that's different here, besides the fact that, that some of the things that the other system makes explicit are more implicit, such as the creation of cells. The main thing that's going on here that's interesting is that when you have these things called expression propagators. Okay, and this is basically just a special kind of a propagator. It's not fundamental, but it's built specifically for this purpose. And an expression propagator basically has some inputs and it has a special distinguished input called the continuation. Okay? And this is pretty cool, because what this means is that now we have no outputs on these expressions. An expression is basically a thing that has a continuation going into it, and maybe some other stuff, and that's it. And when it gets a value, it just basically gives it to the continuation, and the continuation takes care of what happens next. Okay, and so the reason this is interesting is that it addresses one rather, well, there's a problem here, one that we sort of skirted around a little bit. So suppose you're writing a scheduler for this stuff, and you have some big complicated network, and there's some cells on one side with some inputs going into this thing. Okay. And on the other side, there's some outputs coming out. Okay. Now, if you don't know anything about what's going on in this big black box, then what's going to happen is that you're going to be interested in these things coming in the output, and you're going to fill in some of these, and then you're going to say, well, how do we optimize the execution of what's inside here? Okay, because we don't know that there aren't, maybe there's some paths that go, maybe we're only interested in this particular one, and we don't care about those. Okay, and how do we actually execute it so that only this one is being run and not the other ones? Or maybe there's some other stuff being generated in here that we're never going to depend on because of the particular way we put together these networks. Okay, so the question is, how do you decide, given some very complicated graph, which part of the graph has got to be run, which is the job of the scheduler? Okay, and in the general case like this, it's very difficult, because effectively what you're saying is you have to sort of pull things from this side and you push them from that side, and somewhere in the middle they meet. And that's effectively this complicated graph algorithm that's hard to deal with. Okay? Now instead, if you have continuations, what you can do is you can make one of the inputs be the thing that says what you want. And you can shove it in there, and it propagates forward. And all you ever have to do is just propagate forward. And you never have to decide you're going to pull. You don't have to guess what's happening on the output, because you just told it what you wanted. You gave it an object, you piped it into your network, and eventually it gets called. But all the scheduler has to do is keep pushing things forward. Okay, so that's the main innovation that this other model has got, that you sort of turned the data flow on its head by thinking about these things that we're calling continuations. Okay, they're not quite.
Continuation is is a request.
It's a request, that's right. We call it continuations because we're looking at this in the context of scheme, but they're not really like scheme continuations, right? It's a request for a value. It's a message that we're sending into the graph and telling, fill this in, please. Okay? So that's the cool thing here. And what else is there to say about this? So constant is simple. All it does is when you get the continuation coming in, you run this thing, you shove this, you have the abstraction here called return, but basically all it does is shove the object into the continuations terminal, or cell, basically, and we're done. In the case of a variable, we have something a little bit different. A variable has got a name, and it's going to eventually be hooked up to something. And so when the variable is an input, in effect. So we have a propagator. A variable is just a propagator that takes an input and a continuation and takes the contents of the input the cell, the input cell, and shoves it in the continuation. Okay, so it's sort of, it's really kind of a no-op, right? It doesn't really do anything. Okay. Anyway, okay, so let's see what do we have next. So here's the implementations of these abstractions that do. So here's return, pulls out the value from the I got this wrong? You can't value object. Yes, this is something. I don't remember what that does. All right. It's supposed to just shuffle the value around. And I think it probably does because I know this code runs, but I don't remember why one of them is called read and the other one's called write when it sounds backwards. Okay. Here is an example of how if works. And I'm going to this is interesting only because it shows how the free variables are handled. Okay, now a propagator network, what happens is that you have a bunch of variables inside of it, and those variables are inputs. Okay? What ends up happening is that any inputs that are connected up to the input of the, let's see if I can, let me draw this because it might help a little bit. So you get some, so let's say you have two of these expression things. Okay, and inside there's another one like that. Okay, so inside here we have a continuation coming in, and we have some other inputs like X or Y. And then internally we have some other thing that has got an A or a B, and maybe there's a continuation in there too. And we're going to hook some of these up. Let's say we have a B in there too. There we go. We're going to hook some of these up, so maybe this continuation hooks up there, and the X goes to that one, and the Y goes to some other thing. Okay, and this one isn't hooked up. This is a free variable. Okay, this is basically an input that is not connected to an input on the outer shell, if you want to call it that, the outer propagator. This is kind of a propagator abstraction. So anything that is from an internal propagator that's not hooked up to the I/O of the external one becomes a free variable. And so that is what we're going to gobble those up here, like that. We're gobbling up all the free variables of all of the parts of this particular if, and then they're going to become free variables of the combination that we're putting together. And so we keep propagating these things up, and at some point, like here, you can see we're going to be basically connecting them up between the outer and the inner parts. And when we eventually run this propagator network, we're going to have to hook them up first. There's an environment that is kept by the runtime that we plug this thing into when we do the evaluation. It'll have values for plus and minus and that kind of thing. It'll just be plugged directly into that. Okay, and that's how variables work in this compiler, the runtime. Okay, which is, I thought that was pretty cool. Clever, if I do say so. And then we have some other stuff here, which I don't think is very interesting, to tell you the truth. Combinations are hairy, yes? Oh.
Yeah.
Joe.
Lazily instantiated the nested boxes.
This one, I don't actually have the implementation of that here.
Okay.
And the reason is that the one that this one uses is very complicated and doesn't quite work. Someday when I have some time, I will go back and try to fix it and use something similar to what Jerry and Alexi did in their implementation.
Okay. The usual way that recursion is terminated is by making if not be strict.
Yes.
And all the ones you've shown so far, it looks like you do construct a graph that connects up to the consequent alternative for if.
And the cutout here is the combinations.
Yeah.
And so what's happening in this particular pattern is that when you compile something that is a procedure, it is not instantiated yet. It's ready to go, and during the application process, you instantiate it.
Well, the question is, why did you choose to do it that way, and are there unforeseen consequences of doing it that way?
The unforeseen consequence, obviously, is that it doesn't quite work. I mean, it works fine in the absence of AMB, but when I plug in amp and do simple things, it works, but complicated amp patterns were failing. And that was the state I left it in when I stopped working on it a year ago. Because, and the reason I stopped was I came here, so. So yeah, there are some problems with it. I'm not entirely happy with it, but there is a cutout. It just doesn't quite work right. And I suspect that I didn't really understand what was happening there. Okay? Yes, so something kind of broken. And that's buried in this code, actually not in this code, but there's this thing called the apply prop here is the one that actually does that instantiation. And I don't have a slide for that because, again, it gets very hairy. And I really only wanted to talk about the idea that you could do this compilation, and there's no reason why this couldn't be written for the other propagator network. It's just that Jerry and Lexi didn't write one, and I did it for mine, and they didn't. So I think that's about what I had to say for today, which is
Now, I have some
a
things
little
to say
short.
after a break.
We should take a break, and Jerry will come back and we'll talk a little more, but that's pretty much what I had for today.
Okay? I want to talk about philosophy.
Oh dear. Oh dear.